You know, everything around us, yeah, the chair you're sitting on, the phone in your hand, even the tallest skyscraper, it's all constantly speaking a secret language. It's this language of invisible forces and tiny changes that decides if something stands strong or if it completely crumbles. Today, we're going to learn how to decode it.
So think about it. This is the big question for any engineer, right? How do you know for sure that a bridge is strong enough? How can you be positive that a car can survive a crash or that a building can handle a hurricane? Well, the answer to all of that, it lies in understanding just two key ideas: stress and strain.
All right, here's our game plan. First, we're going to look at the internal battle that's happening inside every single material. Then we'll check out the physical response to that fight. After that, and this is the really cool part, we'll uncover a material's entire life story on a single graph. And finally, we'll see how this all becomes the bedrock of modern design.
Okay, so every single time you put a load on an object, I mean like standing on the floor or hanging from a pull-up bar, you're kicking off an invisible war. Inside that material, there's this intense internal force that's pushing back, resisting being pulled apart or being crushed. And that internal resistance, that fight to hold itself together, that's what engineers call stress.
So here's the key thing to get. Stress isn't the force you're applying from the outside. No, it's the internal force fighting back, and it's spread out across the material's area. And the formula? It's just beautiful in its simplicity. Stress, which we use the Greek letter sigma for, is just the force you apply divided by the area it's spread over. That's it.
Let's make this real for a second. Imagine a little steel rod, just 10 millimeters by 10 millimeters, holding up at 10 kilonewton load. Now that's roughly the weight of a small car. The internal stress fighting to hold that load is a whopping 100 megapascals. That number tells an engineer exactly how hard that material is working on the inside.
Now, this internal battle can be fought in two main ways. You've got tensile stress. That's what happens when you pull on something, like a rope in a tug-of-war. The material's insides are literally being stretched out. Compressive stress is the total opposite. It's a pushing, a squashing force, kind of like the stress in the legs of a heavy table. Its fibers are being pushed closer together.
All right, so all that internal stress, it has a real-world consequence. The material doesn't just sit there and take it. It actually reacts by changing its shape. And that physical change, that deformation, whether it's a huge stretch you can see or a microscopic compression you can't, that's what we call strain. Strain, which we represent with the Greek letter epsilon, is really just a way to measure how much something deforms compared to its original size. So if you stretch a rubber band, the strain is simply how much longer it got divided by its original length. And here's a cool thing. Because you're dividing length by length, the units cancel out. Strain has no units, it's just a pure ratio. Here's another super quick example. Let's say we have a 100 millimeter rod and we put a load on it that stretches it by just 1/10 of a millimeter. Well, the strain is just 0.1 divided by 100, which gives us 0.001. Now that seems like a tiny number, right? But for engineers, that tiny bit of deformation is incredibly valuable information.
Okay, so we've got stress, the internal fight, and strain, the physical reaction. So what happens when we plot them against each other? Well, we get one of the most powerful tools in all of engineering, the stress-strain curve. This graph is like a material's biography. It tells us literally everything about its character, from the second a load is applied until the exact moment it fails.
It's really simple. We just put stress on the vertical y-axis and strain on the horizontal x-axis. Then, as we slowly increase the load on a piece of material, we trace out a path on this graph. And that path reveals every single one of the material's secrets.
This journey has 4 key moments. First up, we're in the elastic region. The material is like a perfect rubber band here. It stretches, but if you let go of the load, it snaps right back to its original shape. But if we keep going, we hit the yield point. This is the point of no return. Any stretching after this is permanent. As we pile on more stress, the curve hits its peak at the ultimate tensile strength, or UTS. This is the absolute max stress it can handle before it starts getting thin in one spot, a process called necking. And from there, well, there's only one place left to go: fracture. The material breaks.
Now, here's a quick but really important detail. You might look at the typical engineering stress curve and see that it actually dips down after that peak strength. And you might think, wait, is it getting weaker? Well, not really. That's just because the calculation is always using the original area of the material. But remember, it's necking, it's getting thinner. So if we calculate the true stress using the actual shrinking area, we'd see that the stress inside keeps going up and up and up, right until it breaks.
So, we've just read a material's entire life story on a single graph. Why does this matter? Why go through all this trouble? Because this curve, this simple line on a graph, is the absolute foundation of modern engineering. It's what allows us to predict with incredible accuracy how something will behave in the real world. It's the key to preventing disaster.
Just think about what this one curve tells us. Its strength, that's just how high the curve goes. Its stiffness, or how much it resists bending, that's the slope of that first straight line. Its ductility, which is basically how much it can stretch before it snaps, that's how far the curve goes to the right. And its toughness, its ability to absorb energy from an impact without breaking, that's the entire area underneath the whole curve. It's all right there.
Now, with all this amazing knowledge, engineers don't design things to operate anywhere near their breaking point. That would be crazy. Instead, they define a much lower working stress. Then, they apply what's called a factor of safety. It's basically a multiplier that ensures the stress in real life is always way lower than what the material can actually handle. It's how we build that crucial safety margin into everything from airplanes to bridges.
So the main thing to take away from all this is that the stress-strain curve isn't just some boring graph from a textbook. It is the fundamental blueprint that allows us to build a safe, reliable, and strong world all around us. It's that important.
So we've unlocked the secret language of stress and strain. We can now see how a material is going to behave under a load. But this just opens up a whole new set of questions, doesn't it? Why do some materials snap like glass while others stretch out like taffy? Why do they fail differently under different kinds of forces? To answer that, we'd have to dive into the different theories of failure. But you know what? That's a story for another time.